Hello and welcome back to the video series for Mr. Billingham's BC Calculus class. We're looking at the final piece of the Taylor series material, Taylor series with remainder. Let me start with an important caveat. In 2020, because the school year was somewhat truncated, the AP people have decided that this material will not be covered on the content that you're responsible for on the AP exam. So this is additional material for you, and it is a little bit challenging, but those of you who are interested in science and math type courses as a career and want to go on in further calculus in college would probably be benefited by just at least listening to this material. You can also see there are several problems on the AP free response that we're practicing that this would allow you to look at. All right, so let's begin. First of all, I want to remind you of what a Taylor series for a function looks like. A Taylor series for a function at x equals a looks like this. You should be pretty comfortable with that. That is Taylor's formula for finding a Taylor series for a given, which is a polynomial, infinite polynomial that matches a given function f on the interval of convergence. So now let's look at the new piece, the Taylor series with remainder. Notice a couple of key differences. First, the Taylor formula up here is an infinite series. It goes on forever, and every term has the same form of the terms before it. Down here in Taylor's series with remainder, we stop at the nth term, and then we have a single term which represents the remainder. That is the truncation error. And we have a formula for that truncation error down here. Talk a little bit more about that in a minute, but first, key difference, Taylor formula is a formula for an infinite series. Taylor's theory with remainder has nth degree polynomial and then an n plus 1th degree remainder term. Now, secondly, that remainder term looks very, very much like what you would expect if you went one more term, except instead of having the n plus 1th derivative at a, they have the n plus 1th derivative at c, where c is some number between a and x. Now, I know this is pretty confusing, so I'll give you some examples. Let's take a look at the remainder term. So, the remainder term is this. And one thing that's worth pointing out, when it says r sub n, that's because we're keeping the first n terms. And the r sub n term looks a lot like the first term we left off. And this looks like the n plus 1th term of the Taylor series, except instead of having an a, we have a c. And remember that c is somewhere in between a, which is the center, and x. And since a is 0, we know here that c is somewhere between a and x. Now, what happens as n approaches infinity, as we take more and more and more terms, to r sub n of x? Well, the interesting thing is it looks like that really nasty looking expression it might be really hard to figure out, but this original function is the sine function. And so we know for sure that any derivative of a sine function is going to be a sine, a cosine, a negative sine, or a negative cosine. So we know the absolute value of this expression is less than or equal to 1. So let's look at everything else. Let's look at the x to the n plus 1 over n plus 1 factorial. Now let's, just for the sake of argument, let's say that n is 20. So what does this look like? Well, x to the n plus 1 is 20 to the n plus 1. And in the bottom I have n plus 1 factorial. Now it's not really clear what happens at first, but if you think about it, as I take more and more and more terms, when n is 0, this is 20 over 1. When n is 1, this becomes 20 squared over 2 factorial, which is I'm multiplying by 20 over 2. Then I multiply by 20 over 3. Now, you'll notice so far the product keeps growing. But at some point, I'm going to get, in fact, when n is 19, I'm going to get to times 20 over 20. And then the next term, 20 over 21, I shrink. And then I shrink some more. And then I shrink some more. So basically, the top is just all 20s. But the bottom is a product of numbers that keep getting larger and larger and larger. So eventually, this is going to head to 0. And since the remainder heads to 0 for any x, we show that sine converges to the Taylor series for sine, or rather, the Taylor series for sine converges to sine for all real numbers x. I hope that made sense, or you can just take my word for it. Here's another problem that I will do two different ways, and I think you'll see some logic coming out of this. Here's the problem. So suppose I just use the first two terms of the Maclaurin series for natural log of 1 plus x to approximate f of 0.1. Let's find a bound on the error two different ways. So first of all, how am I going to get the Maclaurin series for natural log of 1 plus x? Well, one, I could do it by brute force. I could use the formula. I could calculate f of 0, f prime of 0, f double prime of 0, and so on. Or I could memorize it, or I could remember how we got it. And that's the path I'm going to take. So I'm going to do a little reminder here. Natural log of 1 plus x's derivative would be 1 over 1 plus x. And 1 over 1 plus x has that a over 1 minus r geometric series feel. So that's how I start. So from the formula a over 1 minus r is a plus ar squared dot dot dot, we know that this would be a power series for 1 over 1 plus x. But it would only converge when the absolute value of r, which is the absolute value of negative x, is less than 1. But in this case, we're trying to figure out f of 0.1, and that's definitely less than 1. So what I would do to get natural log of 1 plus x is integrate both sides. And I'd get this. Well, technically, I'd get this plus c because I am integrating both sides, and it's not a definite integral. But I can check what c is pretty easily by letting x be 0. If x is 0, the left side is natural log of 1 plus 0, which is the natural log of 1, which is 0. And if x is 0, every term with an x in it will go to 0, so we get c is 0. All right, so we're supposed to take just the first two terms of this series, and we're supposed to figure out the remainder when x is 0.1. And we just want to look at the first two terms. But if we look at all the terms, I want you to notice that there's an interesting thing going on. One, the terms alternate in sign. positive, negative, positive, negative. Second, they decrease in size. The first one is 0.1. The second is minus 0.01 over 2. And the third is 0.001 over 3. And finally, the limit of the nth term is 0. Well, those are the three conditions of the alternating series remainder theorem, or error-bound formula. When the series alternate in sign, gets smaller and smaller with a limit of 0, you can choose the first term that you left off as a bound for the error, and that is 0.001 over 3. And that's 3.33 repeating times 10 to the negative 4. So that's the first way of getting the error. The next way is to look at, since I'm keeping the second degree term, I want to look at R2 of x. So R2 of x, using Taylor series error term, is the third derivative of f at c, x cubed over 3 factorial, where c is some number between a, which is 0, and x. And here x is 0.1. So c is a number between 0 and 0.1. So let's figure out what is the third derivative of natural log of 1 plus x. So x was 0.1, and c is somewhere between 0 and 0.1. So the trick in figuring out what's a bound for the remainder is to try to make this remainder term as large as we possibly can. And the fraction 2 over 1 plus c cubed is going to be as large as possible when the denominator is as small as possible. Making the denominator smaller always makes a fraction bigger. And so to make this denominator as small as possible, we want to make c 0. And this gives us 2 over 3 factorial, which cancels, leaving a 3, and the numerator is 0.1 cubed, or 0.001 over 3. So it's pretty interesting, but we got the exact same answer two different ways. One by using the alternating series error bound, and the second by using the Taylor series remainder formula. I know whenever I have a chance, I always use the first method because it's always easier. In this case, we can actually compute the error in using the polynomial because I can take my calculator and make the following calculation. And the calculator tells me that the difference between the correct value of natural log of 1.1 and my approximation using my x minus x squared over 2 formula, the first two terms of the Maclaurin series at 0.1, the difference between those is 0.0003117, which is less than 0.000333, which is the bound that we put on it using the two different methods. So now let's go on to another example. One last example should be enough for us to sort of put this to bed. So this is a pretty straightforward problem. You'll see in a minute. And it has a real feel or flavor of sort of an AP question on this topic. They've given us this time, instead of having to figure out what is the formula for the third derivative of x, of f at x, they're telling us that it's less than 2.3. So let's take a look at R2. Right? Because we can see we're taking the difference between f of x and the second degree Taylor polynomial for x. So that means we want to look at R2, and the formula for R2 is this. And x is in the interval 2 to 2.5. So let's make everything in here as bad as we can and see how large it gets. So this first term, f to the third power of c, since c has to be in the interval 2 to 2.5, it is less than 2.3. And what's the worst x minus 2 cubed can be in the interval 2 to 2.5? Well, it would be 2.5 minus 2 cubed. And then we have over 3 factorial. So I have 2.3 times 0.5 cubed over 3 factorial. And I'll just do that on a calculator. And you can see that this is clearly less than 0.05, which is what we needed to show. Anyway, I think that's enough examples for the Taylor series with remainder. I'm certainly glad to get past this section. Remember, it is not covered on the AP this year, but you feel free to try some problems with it as you run into them as you practice for the AP. Stay safe. Until next time, goodbye. Miss you guys. Anyway, bye-bye.